still joining.
Okay, so hello everyone. I'm glad to introduce the talk of today by Adam Chapman from Academic College of Tel-Aviv-Yaffo, Israel. He's going to talk on roots and critical points of Cayley-Dickson algebras. Please.
Thank you. So hello everybody. So as the title suggests, I am going to talk about roots and then about critical points of polynomials of Cayley-Dickson algebras. But before we talk about these things, let's talk about Cayley-Dickson algebras just to make sure we're all on the same page. And then we'll gradually move towards roots and see what we know and what new stuff we have. So before I start, I should stress that I'm going to talk about only real anisotropic Cayley-Dickson algebras. So what do I mean by that? I mean Cayley-Dickson algebras whose norm forms are anisotropic and they're all constructed over the reals. So the field of real numbers is the center of these algebras. Of course, you can generalize things. You can start with different base field and make the Cayley-Dickson doubling using other elements than -1, but it will make things more complicated. And I think for this talk, it's complicated enough this way. So I'm starting with A0, which is the field of real numbers. And this field, as any field, has a natural trivial involution. And this involution just maps every element to itself. And then you define a sequence of algebras using the Cayley-Dickson doubling. So given some AM minus 1, we're defining AM to be an algebra whose dimension is twice as large. So as a vector space, it's just the original algebra plus another copy. But then we need to define the multiplication table, and that we do in the following way. We take an element and another one, both are, again, some Q plus REM and S plus T times EM, where Q, RS, and T belong to the lower algebra. And the multiplication rule is that this thing is equal to Q times S minus T bar times R plus, here we have T times Q plus R times S bar times EM. So that defines a larger algebra. We'll talk about its properties in a second. But before we do that, I need to point out that you have also an extension of the involution, and the involution is extended in the following way. Q plus R times EM bar is Q bar minus R times EM. Okay. And in addition to the involution, you have now the trace form, which maps every element to itself plus its conjugate, and that's always a real number. And the norm form that maps the element to the element times its conjugate, and that's again a real number. The norm form is a quadratic form, and the norm form is always isometric to a quadratic form whose a diagonal form whose coefficients are -1. Sorry. A -1 if you just take the squares. Just once. So so that gives you some Euclidean metric on the algebra. And one of the nice property is that every element satisfies the following equation. So Q squared minus the trace of Q times Q plus the norm of Q is equal to 0. So every element lives inside a quadratic extension of the real numbers, and this extension is isomorphic to the complex numbers. So you have infinitely many copies of the complex numbers embedded into the algebra. And the algebra is quadratic in that sense. So that's the main asset of these algebras, in my opinion. If you start now with this base field, then the first step gives you the complex numbers. Second step gives you the quaternion algebra. Third step gives you the octonion algebra, and then the Sedanians, and so on. So that's a family of algebras most people heard about. The real numbers is a very nice field. It's an ordered field. Here we lose the order, so it's not ordered. Here we lose commutativity, so it's not commutative. So non-commutative algebra, it's a non-commutative division algebra, but it's still associative. Here we lose associativity, so it's not associative anymore, but it's still a composition algebra. What do we mean by a composition algebra? We mean that until at this point, if you take the norm of Q times R, then this is always the norm of Q times the norm of R. So all these algebras are composition algebras, but here we lose this property. So this is not a composition algebra anymore. And the argument is quite easy. You can take, let's say, alpha being E1 plus E10, and beta being E7 plus E12, where those E's are the standard basis of these algebras. So you start with E1, with E0 or E0, which is just 1. Then E1 is going to be the complex I. E2 is going to be the quaternion J, and then E3 is I times J, which is usually called K, and so on. This way you build whichever basis for whichever Cayley-Dickson algebra you want. So you take the standard basis. Alpha is E1 plus E10, beta is E7 plus E12, and then alpha times E beta turns out to be 0. And the norm of alpha times beta is the norm of 0, which is 0, and that's certainly not the norm of A times the norm of B, because this thing is 2 times 2, which means 4. So that's why the Sedanian algebra is not a composition algebra anymore, and it makes it somewhat less interesting from this point on. However, in recent years, especially in 2019, there were some papers published in physics, in elementary particle physics, about the applications of Sedanians to physics, and it seems like there's a lot of information that can dig there. So we do have some motivation to study these algebras, even though they're not composition algebras anymore. Now, colloquially, people say that the Sedanian algebras and the other higher Cayley-Dickson algebras are not division algebras. That's not true. Every element, every non-zero element is invertible. Alpha and beta do have inverses. They're just also zero divisors. It just means that the loss of associativity creates problems. Some of our intuition gets lost when we have such an algebra with absolutely no associativity. Okay, so that's a brief introduction to Cayley-Dickson algebras. By the way, if anybody has, usually we keep questions for the end, but if I'm saying something which is simply wrong, or there's something that is completely incomprehensible, you can stop me and ask me a small question. Okay, so we are going to talk about those AMs, and these are the Cayley-Dickson algebras we are talking about, and now we want to talk about polynomials. So there are several different ways of defining polynomials. Already over the the algebra of quaternions, there are some issues, right? Because you can decide that the variable or the indeterminate is non-commutative, and then it's in some ways more interesting, but it's also way more complicated and you can barely do anything. So what we do, and that's what people usually do in the literature, so if you go to Jacobson's or Wedderburn's works in the field, then you just define polynomials this way. You take this Cayley-Dickson algebra that you want, and you tensor over the reals with a ring of polynomials over the reals. So without explaining what tensor product means, I'll just say that in this construction, x behaves like a real number, which means that x commutes with every other number. So all the commutators that involve x are 0, and it also associates with any other pair of elements. Every associator with x is 0. And still, it's an interesting construction. It's some kind of a generic central extension of the algebra, right? So this x, especially if you work over more interesting fields than the reals, then x, by taking the right quotient, you can have a central extension by any algebraic simple extension of the base field. So there's a reason to consider these polynomials. And since x behaves like a real number, you can always put all the x's on the right-hand side. So you have a polynomial that always looks like Cn times x to the n plus whatever, up to C1 times x plus C naught. You can always put all the x's on the right-hand side. And then you have a substitution rule. The moment you put all the x's on the right-hand side, you can decide that that's where you put whichever element you want. So if you plug in alpha, you just replace x with this alpha. So I'm going to start by writing it this way, and then somebody might jump and say that I'm writing nonsense, and I do. I am writing nonsense here because what does this mean? If we have no associativity, we cannot just write it this way, but what I'm actually intending to do is to write Cn times alpha to the n in brackets. I didn't mention that, but all the Cayley-Dickson algebras, even though they are not associative, they are power associative. So you can always take the nth power of alpha, and that's well defined even without brackets, and then you multiply this thing from the left by Cn. So that's how we plug in elements in the polynomial. So what do we mean by roots? We say that alpha is a root of f, and here I'm just being a root of f is like belonging to the set of roots, which I denote by R of capital R of f. If plugging in alpha gives you 0. Okay? That's what we mean by a root here. And the basic question is, why do we care about roots in this setting? And that's a legitimate question. And I think the motivation comes from what we know about composition algebras. So I'll start now by talking about what we know about composition algebras. So now I'm restricting the discussion in the next 2 minutes to the case of m less or equal to 3, which means that am is composition. So here we do know several things. One thing we know is that alpha is a root of f. If and only if you can factor out from f a linear factor of the form x minus alpha. So that's already a good reason to study roots. If you have a ring and you want, for whichever reason you study this ring, you have a ring that you believe is interesting and you want to decompose elements into irreducible components, then that's the way to do it. You find the roots. Whenever you find a root, you can factor out a linear thing, which is obviously irreducible, and you keep going. You take G and you factor out another thing, and so on. I'll talk about what's happening in the more general case later, at least what we know. But that's what we know for the composition algebra case. Now, how do we find these roots? So for composition algebras, we actually have an algorithm, and it works this way. So if alpha is a root of f, then alpha is a root of its companion polynomial. And what do we mean by a companion polynomial? I need to explain. So the companion polynomial has several different definitions, but in this context, the easiest one is just to say that it's actually the norm of f. So it's what you get if you multiply f by f bar. So this algebra inherits the involution coming from here. It just acts trivially on x. Okay? Then if you take f and you multiply it by f bar, you have the norm of f, which is what we call the companion polynomial, and it has real coefficients, and its degree is twice as large as the degree of the original polynomial. So if you start, for instance, with the quadratic polynomial of the octonions, then the companion polynomial is a degree 4 polynomial over the reals. So it's not a major catastrophe. That's the kind of polynomials you get here. And these polynomials you can really solve. You have at least, if it's up to degree 4, you even have analytic solutions. Otherwise, you have numerical solutions. It's quite easy to find roots of polynomials of high degrees of the reals, using computers at least. So that's one way, but there's also the opposite direction. The opposite direction is that if alpha is a root of the companion polynomial, then there exists a beta which is quadratically equivalent to alpha. I'll explain what it is in a second, such that beta is a root of the original polynomial. And by that, I mean that the trace of beta is the same as the trace of alpha, and the norm of beta is the same as the norm of alpha. So inside the corresponding copies of the complex numbers, they represent the same element. That's what I mean. And that's also the way, so the algorithm is really, you start with the original polynomial, you switch to the companion polynomial, you find all the roots there. Each root represents a quadratic equivalence class where you can find the original root of the original polynomial. And how do you do it? You just use this quadratic equation that we mentioned earlier to reduce the original polynomial to a linear polynomial, and then you solve it and you find the representative in that quadratic equivalence class. Another important thing to point out that any root of f satisfies one of the following two things. One option is that any beta equivalent to alpha is also a root of f, in which case we say that alpha is a spherical root, and you can say that alpha belongs to the set of spherical roots of f. The other option is that alpha is the only representative of that class that is a root of f. So that means every beta equivalent to alpha that is not alpha is not a root of f. What does it mean about products of linear factors? That's an interesting question. I'll mention an example later on, but it creates some funny things about polynomials. So in this case, we say that the root is isolated. So we really have only those two examples. In the composition algebra case, it changes in the arbitrary higher dimensional case. One last thing that is worth mentioning, even though I'm not going to talk about it much, is that the moment we're working in this setting, you can always get a full decomposition into linear factors. So you can write f as x minus alpha 1, and then inside these brackets you have another factor, x minus alpha 2, and then here you can find some x minus alpha 3, and so on, depending on the degree. So that's what we know, at least most of the interesting things we know about roots in the composition algebra case. So out of all this story, what do we know in the non-composition case? So from now on, I'm going to focus on n greater or equal to 4. Okay, so our AM is not composition. Let's see what catastrophes we have. So among those things, I'm going to focus on number 2 for the moment. That's, I think, the main result we have. It's not like the other things are not interesting. We just did not consider them in the paper, at least not explicitly. So is it true that over the Sedanians, for instance, if you have a root of a polynomial, then it's also the root of the companion polynomial? And the answer is no, it's not true. So 2 is false. Let's see an example. Take the same alpha and beta we had earlier. So we have this E1 plus E10, and beta is E7 plus E12. I think almost all the easy counterexamples we can just produce by just picking those two. So let's just look at f equal to alpha x. So clearly beta is a root of f, because if we plug in beta, you get 0. But what is the companion polynomial of f? So you multiply alpha x by alpha bar x. X is central, so you just get alpha times alpha bar, but alpha times alpha bar is 2. So you have 2x squared. Yeah. So if you plug in beta here, you just get 2 times beta squared. Beta squared is -2, so you get -4, and that's not 0. So beta is not a root of the companion polynomial. So that's a very easy counterexample to 2. So already this connection, this nice connection between polynomials and the companion polynomials gets ruined when you switch to the higher Cayley-Dickson algebras. Does it mean that everything is lost? So not everything is lost, but certainly a lot of things cannot be obtained. So this a miraculous thing that you can always switch to polynomials over the reals, do everything there, assuming that you'll find solutions of the complex numbers and coming back, that's not going to work. However, there is a special type of roots that do carry out over this thing, and these are the spherical roots. Here it's also a good point to say that we did not say that out loud in the paper, I think, but that also gives an example, a counterexample to 4. So if you think, is it true that every root of f is either isolated or spherical, then it's already not true in this example, because in this example, beta is a root, negative beta is a root, but beta here is actually quadratically equivalent to alpha, and alpha is certainly not a root of f. So it gives you also a counterexample of the fourth property I mentioned. So there are many things that don't work. I'm not going to say everything. I'm not going to go over all the things that don't work. I want to say something positive. So what can we say? There is a theorem that we proved, and by we I mean friends here. So it's Alexander Guterman and Vishkautsan and Svetlana Zhilina. And the theorem that we proved is that if alpha is a spherical root of f, then it's a root of its companion polynomial. It sounds like it should be easy, but apparently it's not super easy. I'm not saying it's super hard, but it did require some effort in certain places. So I'm not going to give the entire proof. I'm going to mention the main lemma that helps us solve it, and perhaps talk a little bit about its proof. So what is the lemma? The lemma is actually some kind of an analog to the property number one here. So we have this rule of how you can pull out a linear factor if you have a root. It works both ways. And the lemma says the same thing, just about spherical roots, but this lemma actually holds true for any Cayley-Dickson algebra. And the lemma says that alpha is a spherical root of f, if and only if you can factor out a quadratic polynomial. And this quadratic polynomial, surprise, surprise, is the one that you would expect. It's x squared minus the trace of alpha times x plus the norm of alpha. Okay. And even this lemma is not super easy. So one direction is relatively easier. If you want to talk about why being a polynomial of this decomposition implies that alpha is a spherical root, that's actually a straightforward computation. You can find it in our paper. It's really not illuminating in any way. In the opposite direction, it requires a little bit more effort. So what we do in the paper is quite elaborate, because we want to make it as general as possible, and we actually do study the general case of the general fields. But here, if you want an easier argument just for anisotropic Cayley-Dickson algebras over the real numbers, then what you can do is just take f, divide with remainder by x minus alpha. Divided with remainder by this thing, this quadratic thing, then you are left with some remainder. So you have f is g times this quadratic thing, plus some remainder of the form gamma x plus delta. And then you use the following trick. You say that, okay, alpha is spherical. So all the elements that are quadratically equivalent to alpha are also roots of f. Now, gamma lives inside some complex algebra. You can choose this complex algebra to be, you can choose alpha to be, you can choose an element equivalent to alpha inside this complex algebra, and you plug it in this thing, and then this thing disappears, and that thing should be equal to 0. And then you can also plug its conjugate inside this complex algebra, and that implies that both delta and gamma are going to be 0, and that's how you get that the remainder is 0. So you have you can just use division with remainder by this quadratic thing. You pick an element quadratically equivalent to alpha inside the complex algebra containing gamma. You plug the element, you plug its conjugate. Both are roots of the polynomial, and therefore you get that the remainder is 0. So that's a proof, hand-waving description of the proof of this lemma, but it's really not difficult if you stick to the real case. The more general cases, again, more elaborate, you can find the argument in the paper. But the moment you have this lemma, then the proof of the theorem is quite easy. So you take alpha to be a spherical root of f, and then f decomposes as g times this thing. Instead of trace of alpha, I'm going to write t. Instead of norm, I'm going to write n. And then if you compute the companion polynomial, then what you get is g times this thing times the bar of g times this thing. However, this guy is central, so you can just take it out, and it's immune to conjugation, to the involution, and eventually you get g times g bar. It doesn't matter, it's exactly the same. G bar times g, g times g bar times this polynomial. Well, so you have a right factor of this polynomial, and that means by the same lemma that alpha is a root of the companion polynomial. So at least when you want to find the spherical roots of a certain polynomial, you can use the companion polynomial. It does not mean that every root of the companion polynomial is a spherical root of the original one. Of course, you can produce easy counterexamples. Just take x minus I. Certainly, j is not a root, but I is a spherical root of the companion polynomial, which is x squared plus 1. Easy examples exist already over the quaternion algebra. Okay, so I think that's what I want to say about roots. Now, what do we have about critical points? I need to explain what critical points are, because the definition is not obvious, right? If it's even over the complex numbers, it's already not super obvious, because there are you could take in principle for polynomials it works, but in general for functions it might have a derivative in a certain direction, but a different one in a different direction, and you really need something that captures everything together to say that it's analytic at a certain point. For polynomials it's easier, but it's not working already of the quaternion algebra. So here we talk about the formal derivative. Okay, you have a polynomial, and its derivative is just taking, you have x to the n, so you take the n down as a coefficient, so you have this guy, and then the power is reduced by 1, and you end up with C1 instead of C0. So that's a formal derivative. What does it mean? I'll say in a second. I'll just say that critical points is what you expect. A critical point of f is just a root of the derivative. Okay, it's a point where this formal derivative vanishes. Geometrically, what do we mean? So you have the Cayley-Dickson algebra, which is certainly not two-dimensional, but I'll draw it this way anyhow. So you have something here. And you have a point here, and it's critical if the derivative in the specific direction of the real axis is 0. Okay? That's the definition of a critical point in this context. I'm not saying anything else here. You have the real axis, and you are moving in this direction. And what I mean is that here you might climb up, but here you are starting to climb down if you walk in this direction. And at this point specifically, you have, at a given moment, you have derivative equals 0. Okay, so that's a critical point. And there are several different theorems about critical points, and we address several different theorems in our paper, but here I'm going to just focus on one of them because I think it's enough for one talk, the Gauss-Lucas theorem. So what is the Gauss-Lucas theorem? Gauss. So it says that the set of all the critical points, I need to say over which algebra. So here we're working in the complex setting. So A2 is a constant. So when we talk about complex polynomials, the critical points of a polynomial live inside the convex hull of the roots of the polynomial. What do you mean? What does it mean? It means that each critical point is some kind of a weighted average of roots of f. Okay, you have different weights on the different roots of f, and like for instance, you can have the point in the middle between two roots. So the classical example is that when you take f to be x minus a times x minus b, the only critical point you have is 1/2 a plus b. Certainly a and b are roots, so you have the midpoint between those two roots. And that's just an example to understand what's going on here. Of course, the proof is more interesting than just this example, but that's the theorem that we are considering. So now, we were not the first people to consider this theorem, fortunately, because it's more interesting to study things that have been studied by other people. So fortunately, Giloni, I hope I'm pronouncing the names correctly. So Giloni and Perotti in 2018, perhaps a little bit earlier, but it was published in 2018, doesn't really matter. They studied the case of A3. Actually, I'm shifted, so here it's actually A1, right? It's not A2, it's A1. Because A0 is the reals, A1 is the complex. So he studied the case of A2, which is the quaternion algebra. So here you can ask several different variations of Gauss-Lucas. And of course, there's a reason for all these variations because both of them are just wrong. The first is asking, is it just true, phrased like that? Is it true that the critical points of a quaternion polynomial are contained in the convex hull of the roots of the polynomial? So here, the answer is no. The answer is no, and they have a very nice, easy example. So you just take x minus I times x minus j. So you remember that I mentioned that each polynomial over like in the composition case, has roots which are either isolated or spherical. So here, j is certainly a root of the polynomial. If I were a root as well, it wouldn't be this polynomial, it would be x squared plus 1. So the mere fact that we don't have x squared plus 1 means that I is not a root of this polynomial. No other conjugate only root of this polynomial. It's quite a nice argument. Of course, you can also do it directly, but the set of roots of this polynomial contains j alone. So certainly, and if you compute the critical points here, then it's like in the previous example, you get 1/2 I plus j. So certainly, it cannot live inside the convex hull of the original polynomial. So that's the naive question. The somewhat less naive version is to ask whether the critical points of f live inside the convex hull of the roots of the companion polynomial. Now I'm a little bit doubtful about what I'm going to say. So give me a second before my brain is completely kaput. Yeah, okay, so I'm not completely senile yet. Yeah, so one option is to ask whether the critical points of f live inside the convex hull of the roots of the companion polynomial, which in the case that they are studying the quaternion algebra, there's no difference between the roots of the companion polynomial and the conjugacy classes of the roots of f. They are the same. So you can take the roots of f, take the spheres, and then these are the roots of the companion polynomials. And here, the answer is usually no, apparently. So it is positive only when the degree of f is 2. In that specific case, it's true. So you have not so many roots, and you can show you have not so many critical points either, and you can show that the critical point lives. I don't think I'll have a lot of time, but if I do have time, I'll explain how we generalize this, and then I'll explain a little bit of the proof here as well. So it's true for quadratic quaternion polynomials. It's not true otherwise. And as an example, they gave the second natural example that you would think of, which is just x minus I times x minus j times x minus k, and k is I times j. I'm not going to explain now how the example works, but it's actually a nice example. So it's usually, so most of the naive generalizations are false. What they also do is to really find a variation that works, a little bit ad hoc, but it still works. So you can say that the critical points, they live inside the snail of f, and I'll explain what this snail is. So again, you have f, and you have different copies of the complex numbers inside of the algebra. For each copy, you take the roots of the projection of f to this sub-algebra. So you get some roots for any such complex sub-algebra, and you draw the boundary and the thing that you have in the interior, and that's this essentially. So the critical points do live inside this snail. It's not quite clear how this snail is going to be computed, but using this snail, you can use certain bounds for the roots. Also, to be implied for the critical points, and then you have at least a compact small sphere to look at, hopefully, if you're looking for critical points. So that works. So that's a theorem that they prove. And what do we do in this context? So here we study AM, A is greater or equal to 3. So number 2 is, again, of course, it's generally false because you can use the same example they used also over the Octonian algebra. But apparently 2 is true, is correct in the following cases. So the first case is again when the degree of f is 2 and m is equal to 3. So here we're talking about octonions. How does it work? The proof is quite easy. So we're using everything we know about octonion polynomials, right? We know that every octonion polynomial decomposes into linear factors, so you can write the polynomial as some c times x. Let's write it nice. So it's c times x minus b, all of that times x minus a. So the derivative is simply going to be c 2 times c times x minus cb minus ca. And the only critical point that you have is again 1/2 a plus b. Now, a is certainly a root of f, so it's also a root of the companion polynomial. B is not necessarily a root of f, but b is conjugate to some, it's quadratically equivalent to some root of f, so b is a root of the companion polynomial of f. You can also compute just the companion polynomial and see that you get x minus b times x minus b bar, and then you can see that b is a root of the companion polynomial. So this guy is midway between those 2 points, which are roots of the companion polynomial, and therefore the theorem is correct. So that's one case. The other case is that an element is in the convex hull of the roots of the companion polynomial if this element is a spherical critical point. So when alpha is a spherical critical point, or in other words, alpha is a spherical root of f prime. So if you take a critical point which is spherical, meaning that every element which is quadratically equivalent to alpha is also the critical point of f, then this element lives inside the convex hull of the roots of the companion polynomial. So that's nice. That's a positive thing, even for number 2, that seemed to be completely incorrect. It's not completely incorrect, at least not for spherical points. And the snail can be certainly extended to any Cayley-Dickson algebra, so that's true in general. And just define the snail more generally for any Cayley-Dickson algebra of any dimension, and you don't need to assume anything about the critical points being spherical, and it's still true. So that's what we did about critical points. The last thing I want to mention briefly is that it's not easy to find the critical points using the snail, of course. It's also not very easy to find the roots because the roots are not, we cannot find them using the companion polynomial. However, you do have a way of reducing the question to finding the roots and the critical points inside certain spheres And the argument is using the snail eventually. So I'll just mention the result. You can say that both the roots of f, so that's a theorem, and it has several variations in the paper, both the roots of f and the critical points, they live inside a sphere of radius. And now the radius can be several different things. One thing, well, I'm assuming here f is monic. So you need for this theorem to assume that f is monic. If you do assume it, then meaning that the leading term has coefficient 1, so Cn is 1. And then the radius is 1 plus the absolute value of Cn minus 1 squared plus blah, 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 all the way to the absolute value of C naught. And you can also have the 1 plus the maximum as an alternative radius of these guys. And some other upper bounds for the radius. And then if by chance the coefficients are not too large, then you have at least a sphere, and then you can hope for numerical methods to work and to find the roots and the critical points for you inside that sphere. And the argument really uses the snail. So I think, and of course, there's more to say, but I think that's enough for now. I think if somebody wants to learn more, then certainly instead of just finding more theorems that you can prove, you better just start by seeing how it works over general fields, because there it becomes more interesting. Okay.
Thank you very much. Let us see if there are questions. Yeah, there is a question in the chat.
Yeah, I see. Is there a reason for calling the roots spherical? Yes, there is. I don't know if it's a good reason, but first of all, I should point out it's not my term. Okay, I did not invent the term. It exists in the literature. The reason is this. So let's focus on the case of quaternions. Okay. So when you have an element alpha, it has a trace and a norm. The trace is actually 2 times the real part of alpha, and the norm is basically the Euclidean norm, right? So you have some beta bi plus cj plus dk, and so the trace of alpha is 2 times a, and the norm of alpha is just a squared plus b squared plus c squared plus d squared. Now, when you look for all the elements quadratically equivalent to alpha, so you're looking for the set of all betas such that beta is equivalent to alpha. What you get is the set of all elements of the same trace. So you have not a lot of, you don't have any room to play with the trace. The trace is going to be 2 times a, the real part is going to be a. So these are elements of the form a plus, and then you have xi plus yj plus zk, such that, and then you have a squared plus x squared plus y squared plus z squared is equal to a squared plus b squared plus c squared plus d squared. So you can just erase the a squared. If you want, you can call this radius squared. and then you just get some kind of a sphere, right? It's like a sphere in R3 of radius R. That's the only argument I can find for spheres. But if you now ignore the central part and you just look at this thing, then this equation, like the equation x squared plus y squared plus z squared equals r squared, gives you a sphere of radius r inside of this copy of R3 inside the quaternion algebra. I see that Seidon also has a question.
Yes, thank you very much for the talk. I have a question. So in case you have spherical roots already, in the case of quaternions, you can factor the polynomial with respect to roots that have nothing to do with the root you have in mind. So is there a way to sort of read off the roots from the coefficients of the factors? Or, I mean, without using the theory. So if you have x squared plus 1 equals 0, you factor it with x minus I, x plus I. Is there a way to see j, say, sitting there without using?
Yeah, that's a good question. In some way, yes, right? Because at least in the example you gave, it's obvious, because if you have x squared plus 1, then
yes, in this example it's obvious, I agree, but in general,
blind to the choice of complex subalgebra, right? So by symmetry, or something that physicists would say, by symmetry arguments, you can say, of course, if it's a more complicated product, if you now multiply this guy by x minus j and by a to the 3 minus k plus, just throwing out numbers, whatever, then you get something that is not obvious how you factor x squared plus 1 from that. And if you just play by the algorithm, then you will probably just find that I is a root of the companion polynomial, and then you will need to do some work. You'll have to plug it in back into the equation and get a trivial equation, which would mean that I is actually a spherical root, and then you can factor out x squared plus 1. So I don't see an easy way, unless it's really easy, unless it's really a central polynomial, and then obviously it doesn't matter whether you choose ij or whichever.
Sure. Thank you very much.
So Artyom has a question.
Yes. Can you hear me?
Yeah.
Okay, I have the following question. At the end of your talk, you mentioned that we can consider the same questions over arbitrary field. So we can start with, say, algebraic closed field, yes. And so in this case, do you know something about critical points, or let's say spherical roots?
Okay, so that's a very good question. So I'll divide the answer into two bits. Okay. First of all, you can study these things over arbitrary fields. To my knowledge, some of the results, even over in the composition algebra cases, I mean, up to octonions, some of the results hold true only when these composition algebras are division algebras. So the moment you choose to work over algebraically closed fields, you avoid this option, right? If you start with A0 being the complex numbers, then already A1 is going to be an étale quadratic extension of the complex numbers, but it's not going to be a field. And the quaternion algebra is not going to be a division algebra. So you don't have division composition algebra. So some of the results are not true anymore.
Yes, yes. For example, if field is algebraically closed, so it will
yeah. If the field is a complex number, so
something quite different.
Actually, I think it is an interesting question to just take even the split case, right? You take an algebraically closed field, you take all this construction, and then many of the things that I said are just wrong. You have many weird things happening just by the fact, even over the quaternions, that you have like upper triangular matrices that are potent and cause problems. And so, yeah, it's just a different direction. So what I'm saying is that some of the results are true. I'm pretty sure that the results on spherical roots are stated in the paper without any assumptions on the base field, so that's going to be true. But some of the classical results are not true, and yeah, it would be interesting to just really take the split quaternions, split octonions, and study again. Let's find the roots, let's find the critical points, and let's do everything in the split case. So the answer is that I don't always know the answer. And that's the answer.
Okay, thank you for your answers. Thank you for the questions as well. As far as I see, there are no more questions. Okay, so if not, we thank the organizers and thank the speaker and thank the participants, and I think we can stop our session for today. So see you all next week.
Bye, thank you.